Hello. So, in this video, we're going to be talking about rates of change. And in particular, we're going to be sort of reviewing, although you may or may not have learned it with this sort of language, average rate of change, and introducing what may seem like a relatively strange concept when we think about it, the instantaneous rate of change. So, sort of as a thought example, let's think about driving in a car, right? So when you drive around in your car, you have a speedometer, and your speedometer is going to tell you, at least hopefully, how fast you're going, right? So the speedometer tells you your speed at any given moment, but when you sort of stop to think about that, how exactly does it do that, right? So this is one of those things that seems obvious until you think about it too much, and then it starts to get really confusing because really the whole point of speed, right, the definition of speed is that it's this change in location over a change in time. But your speedometer is, at least in principle, telling you how fast you're going at a specific moment in time, right, a single point in time. But that seems sort of like that shouldn't work, right? Because by definition, speed needs more than one point in time to know how fast you're going. So how does it do that? Well, the trick is that it's not doing that exactly, right? So what you, the driver of the car, wants to know is really about how fast are you going right about now, right? With these quotes that are going to be doing an awful lot of work without us realizing it. So what the speedometer is actually doing is it's measuring an approximation of your speed at a given time period. And the way it's doing that approximation is that it's figuring out over a very, very, very small time interval how far you go. And then it will sort of do that displacement, right? So it says, okay, if I measure some distance that you travel over some really small period of time, that should approximate how fast you're going for that period of time. And if you make that period of time small enough, this will give us what we think of as a speed in the moment. Okay, so to see what we mean by this, let's sort of do a toy example here. So let's say we have this function, s of t, and this is going to represent how far from a starting line your car is going, right? So we can see sort of with this curve, right, if we just graph the curve, then over time, right, time being our x-axis, so as the time increases, this vertical is representing exactly that displacement, right, how far from the actual point that you are, the starting point. So as you sort of start at time 0, you're clearly sort of driving quickly already. So you're rapidly getting away from the speeding, right? This is rapidly getting away from the starting line. And then at some point you turn around or you sort of stop and reverse, and then you come back maybe about 3 minutes in, okay? So again, the whole idea of speed, right, is how far you have traveled versus how much time it took you to do that traveling. So if we pick a really small interval, let's say 1/100th of a minute. So in practice, your speedometer is actually usually using much smaller time intervals even than that. But if we take 1/100th of a minute and we sort of go around, let's say 0.1, we want to know how fast are we going when we're 1 minute in. So we would do that sort of time interval in either direction. So we're looking at 0.99 minutes to 1.01 minute, right? So we're looking at this sort of a little bit over 1 second interval, which again, actual speedometers do much faster periods of time, but just for our example. Then what your speedometer would do is it would calculate exactly this idea. It would say, okay, you're however far you were at 1.01 seconds, subtract where you started from in our time interval that's much smaller, right? So it's sort of where you ended up is that s of 1.01 versus where you started in our smaller time interval, s of 0.99, so 0.99th of a minute. and then it divides by how much time has elapsed. So 1.01 minus 0.99, okay? So this is going to look kind of messy because it's a big function. So just sort of bear with me. All I'm doing is applying the function here, right? So I have s of t was that input cubed with a negative plus 9 times that input, and then I'm subtracting off when I plug in 0.99, and that bottom I can just simplify to 0.02. So crunch all those numbers together, I get this pretty ugly looking fraction, but nonetheless I get a number which I can simplify to this 5.9999, or roughly, just under 6 units. So we'd have to keep track of the units here, right? So the t was in minutes, and I guess we didn't really specify the distance, but let's say the distance is in, I don't know, miles or something. This would be miles per minute, okay? So this is how your speedometer is sort of determining how fast you're going. It would do some sort of calculation to give it into units that you actually know, like miles per hour. But here's the thing. This piece here, or even this piece up here, should look pretty familiar to you. So on the one hand, I did it just by calculating speed, right? The distance in travel, that's where I ended up versus where I started, and the distance in time is the end time minus the start time. But another way you might recognize this is exactly sort of hunting from math teachers cackling in your past, right? Is this rise over run. So this looks very, very much like a slope formula. And in fact, that's actually what's basically happening here. So what we did is we took 2 points in this zoomed in version of this graph, right? So I have these 2 points along part of the curve. Notice that our axis isn't from 0 like the original one is. So I've zoomed in, and I have these 2 points. But what I'm really doing then is I'm finding the slope between those 2 points, not necessarily on the curve, but on the secant lines. The secant line is a line that intersects a graph in exactly 2 places, for the sake of this sort of calculation. So I have these 2 points. I formed a line that went through those 2 points, and I looked at the slope of that line. That's what that number really represents, okay? This is what we would call the average rate of change. So what I'm really doing is, even though I've taken a small time interval, I am still taking a time interval, and so maybe I was going faster or slower at various points in that time interval, but on average, I've calculated out that 5.9999. That's my average rate of change, or my average speed, okay? If I zoom in a little bit here, there's sort of 2 separate ideas that I want to point out here. One of them is looking a little bit into the future, where we're going to be revisiting this average versus instantaneous rate of change question. You may notice that this curve, the white part, and the green line are basically identical. And in fact, if I sort of move the green line out of the way for a second, these look almost parallel, right? You might be able to detect a slight curve in the white part because this is a secant line. It's not following the graph. It's just going through those 2 points. But zooming in somehow made them look the same. And this is actually a key sort of idea to notice, is that when we zoom into a curve enough, it starts to look like a line. This is something we're going to come up with again and again and again, okay? The other thing that we want to notice is that we basically, so we went through these 2 points, and the way we sort of did that wasn't that we were trying to go through 2 points and find a slope. It's that it was equivalent to thinking of this as a change in time and a change in position, right? So the change in time was the change in the x value, or the t value in this particular graph's case. And then the change in position was that vertical bit, because the vertical bit was measuring how far away from the starting line I was. But this is how we can sort of come up with a general form for this average rate of change. So if I give these points more abstract labels, right, instead of thinking of them as specific points, the 1.01 and the 0.99 that we had before, if I think of them as just abstract points, x1, f of x1, x2, f of x2, for any kind of x1 and x2, then my average rate of change is exactly this slope formula, but applied with those points, right? So I can see I have the x2 f of x2 is going into the first part, right? And the x1, f of x1 is going into that second part, and I'm finding the slope between those two lines, just like this was one of those oh so classic questions of here's two lines, find the line that go, or here's 2 points, find the line that goes between those points, right? So same exact process, but now we have the context to interpret it as an average rate of change. Now, this has all been sort of a description of average rate of change, and as I just explained 2 seconds ago, none of this has probably been particularly new math. It might be a new way of looking at the math, but all of this math is stuff that you've done, mostly even in Algebra 1, certainly by pre-calculus. Most notably, limits have not made an appearance, right? So why are we doing this in calculus? Calculus, as I claimed, is all about limits. So to see where the limit part comes in, then we want to talk about instantaneous rates of change. We want to talk about how do we use this idea of an average rate of change to honestly get an actual estimate of a rate of change at a specific point, which again is sort of paradoxical, this idea that like it sort of needs 2 points. And yet the claim is we can get around that, okay? So in the we're gonna see a little bit of a video and an animation here cutting in that will explain or sort of demonstrate, show exactly how this works, okay? We've seen that calculating an average rate of change is simply the process of calculating the slope between 2 points. Calculating an instantaneous rate of change, then, should be the slope at a single point, right? But there's an obvious problem with this. The slope formula requires 2 different points, doesn't it? Clearly, we have an issue if we try to use only 1 point. So what we will do instead is place a temporary point along the curve to anchor our line and give us 2 points to calculate the slope. This will give us an approximation of the instantaneous slope, but we want these 2 points to be as close as possible. The closer they are, the better approximation we will have of the true instantaneous slope. This is where we're going to do something a little odd at first glance. Remember that the point we placed is there because we want a close by point for the slope formula. In fact, the only real property we care about for this point is exactly how close the point is. For that reason, instead of giving it a label like x3 and f of x3, we're going to label it based on its distance from our point of interest. In particular, we know that it is some distance from x1, and by convention, we will call that distance delta x, written as a small triangle with the x. Thus, the second point is at the x value x1 plus delta x, and its y value is f of x1 plus delta x. Now, we can see that the slope can be written as this, and we could simplify the denominator to just delta x. This makes our trouble pretty clear now, though. On the graph, we can see that if we want to make delta x 0, then looking at our slope formula, we can see that doing that gives us 0 over 0. This is where limits come in to save us. We want to take a limit as delta x goes to 0, which will allow us to see what the slope formula is going to as the approximation gets better and better. That is, as delta x gets closer and closer to 0. Thus, to find the instantaneous slope, we need to take the limit as that distance goes to 0. So, in this video, we talked about average rates of change and instantaneous rates of change. We spent sort of a bunch of time talking about average rates of change simply / especially because of the fact that it's really the same mechanic with a little bit of calculus thrown in for the instantaneous rate of change. So in particular, we talked about rates of change and we computed them and we showed how really what we were doing was just looking at the slopes, right? And moreover, we talked about how the instantaneous rate of change in the real world, really what's happening is that we're looking at sort of an average rate of change over a small time window, right? That's like your speedometer. In practice, this is usually how you actually figure that out. But We also talked about how to compute an instantaneous rate of change in a more abstract sense, right? In a more theoretical sense, using the power of limits. And in particular, we talked about and showed how using limits with that same slope formula in this, what we were going to be calling a difference quotient, that we can sort of merge these points together, right? Get them arbitrarily close. And we use that as a way of approximating our instantaneous rate of change to make it much more accurate than the sort of traditional average rate of change over a small time window, right? Because as we've mentioned in the past, the whole point of limits is to put a more rigorous context on what we mean when we say small, right? So this is how we are going to be doing this moving forward. And in fact, this is going to open up a whole world in calculus. This is one of those things where we're going to be running down the rabbit hole. This one seemingly simple thing, simple question, is going to be what we're going to spend most of the semester doing in practice. Okay, so that is that.